Hey engineering students, today we're going to talk about two components, a 7-segment display and a shift register, and we're going to build them into a project. 7-segment display is something you've probably seen before. Over here on the right you can see this little 7 segments that are all LEDs in this case that can be used to make any of the 0 through 9 10 digits, and this one also has a decimal point on it. These are little individual LEDs. Sometimes these are made of liquid crystal display as well. You've probably seen them on like a microwave or an old-fashioned clock radio at your grandma's house, or calculators sometimes have these 7-segment displays on them as well. And a shift register is an integrated circuit that can be used to control this 7-segment display. So here's the basic idea. What we're going to do is we're going to make a prototype that will count down on this 7-segment display from 9 to 0, all 10 digits in the decimal number system. And the Arduino will control that through the shift register. So that's what we're after today. That's the project that we'll be working on. So things you're going to need for this project: you'll need many jumper wires. There's a lot of connections. It's a complicated circuit. And you're going to need this integrated circuit, 74HC595, or a 595 chip for short. And this is an integrated circuit that has on it the shift register. Sometimes it's called a serial to parallel converter. This is a kind of a standard package for an integrated circuit. It's what's called a dual inline pin, or DIP chip. It's got on both sides of it some pins. Those are the connections to the internal circuitry, and each pin has a specific purpose and is connected to certain transistor-based components on the inside of the circuit. You're going to need a bunch of resistors because we have to protect all the LEDs, so we'll need 8 resistors altogether. And then you're going to need a single-digit 7-segment display. Those are the things that we're going to need for this project. Let's talk about the 7-segment display for a little bit. So if you think about this 7-segment display and how it can be used to make all of the digits in the decimal number system, you can think about which segments would have to light up if you wanted to display certain numbers. Let's say a 0, for example. To make a 0, you'd have to light up segment A and B and C and D and E and F. In fact, the only segment that wouldn't be lit up would be segment G. So with all those LEDs lit up, you'd make basically the shape of a 0. How about a 4? If we wanted to make a 4, we would light up F, and then we'd light up G, and we'd light up B, and we'd light up C. And it makes kind of the shape of a 4. It'd be recognizable as a 4. So now we can see the pin connection. So this 7-segment display is going to have 10 pins coming out of it, and each one is connected to a certain spot. The pins, pin 1 is in segment E, as you can see on here. There's a connection between pin 1 and segment E. Pin 2 is connected to segment D. Pin 4 is C. Pin 5 is the decimal point. 6 is segment B. 7 is A. 9 is segment G, that one in the middle, and then 10 is segment, 10 is the segment in the middle, that's G, and 9 is segment F over here on the upper right. That's pin 9. So that leaves 2 pins that don't have any connections, and those are the ground connections. So pin 8, we could connect that to ground, or pin 3 could also be connected to ground. Down on the bottom we have 2 options. So this is what's called a common cathode 7-segment display. Common cathode means the ground pin is common for all the LEDs. So the internal circuitry in this component has the positive side, the anode side of each one of the LEDs that make up this display come from those pins, and then all of them are wired to the same ground, or the same negative terminal on the display. So that's how that works. So if we wanted to make a 0, for example, we could turn on all of the pins except for the decimal point pin 5 and the middle segment pin, which is 10, and then we would display that. All those lights would be lit up. So to tell which ones would have to be lit up, we could make a table and think about each of these segments and how they would have to be high or low to make the display show what we wanted to display. So we've already gone through 0. we would need all the segments except for G and the decimal point. So those would all be 1s except for G, and decimal point would be 0s. If we wanted to make a 1, well, only B and C would be lit, and everything else would be low. So we'd have all 0s except for B and C would be on. Let's say we wanted to make a 2. If we want to make a 2, we would want A, B, G, E, and D to be all high. So that would be a 1, 1, 1, 1, and 1. And then the remaining inputs would be 0s. So we can get a string of 8 1 or 0s. That's a combination that makes us light up our LED the way, our pattern of LEDs in the 7-segment display to show the digit that we want. Each one of these choices between 1 and 0, each one of these digital choices is what we call a bit. And a string of 8 bits is what we call a byte. And so we're going to use a byte of information to control this display when we start programming our Arduino to control this thing. Now let's take a look at the shift register, or the series to parallel converter. Before we start talking about how this works and how we code it or how we connect it up in our circuit, I want to use a little analogy to show you how this thing works. Imagine that we have a train, and I'm just going to draw my crude version of a train. So this is a 3-car train that I'm making. So this train goes into a tunnel. And this is a complicated tunnel with some stuff inside of there. And what this tunnel does is it takes train car 1, 2, and 3 that are connected to each other in a series, and it splits them up. And it takes car number 1 and it puts car number 1 in its own spot on the tunnel, puts it on its own track. Car number 2 comes into the tunnel, gets broken up from the train. Car number 2 ends up on its own path as well. Car number 3 gets taken off the train. Car number 3 ends up on its own track. So once the cars are in the tunnel, they get split up from each other, and they're no longer in a serial train, but instead they're parallel to each other, and each one comes out of the end of the tunnel on its own track. So the train is like series data. The data is in a train, one bit right after the other, and if it's a byte, that's an 8-bit train. The series to parallel converter, the shift register, has the function of splitting up the train and then putting every one of the bits on its own track so that it comes out the end of the tunnel separate from the others, not part of a train anymore. So it's parallel instead of series. That's the basic idea, just based on an analogy. So how does it work? Well, we have a pin on this shift register, on that chip, called the latch pin. And when that gets put low, and we write it low from the Arduino, that opens up the shift register. And that means it allows new data to come in to this sort of a storage place. Now, on 2 other pins, some other information is coming in. One of these pins is called the data pin. And that pin has got a series of bits on it, 1s and 0s, and we're representing them here on this graph kind of as a high, which could be thought of as plus 5 volts on the graph, and a low, which could be thought of as 0. So it's a 1 and a 0, 1 and a 0, 1 and a 0. So that's the data stream that's coming in. So this is your train. Each car is one of these numbers. It's either a 1 or a 0. The other information that's coming in on a different pin is called the clock. And this clock is just 1 0, 1 0, 1 0, 1 0 in a regular repeating pattern. So each time the clock pulses high, what that does is it reads the data stream to find out what bit do we have there. Is it a 1 or is it a 0? And then it pushes it into one of those tunnels. It pushes it into a location in that storage spot. It's like a little bunch of shelves kind of. So in this case, clock pulses high, it reads the data stream, data is a 1, and so it puts a 1 in that first little cubby hole in the closet. And then the clock advances, and the next time it pulses high, it reads the data again. This time the bit is a 0, so it puts a 0 in the next location. And then time advances and the clock pulses again, and it reads the data stream on the clock pulse, and it sees a 1, so it puts a 1 in, and then another 1. Clock pulses again, it's a 0, and a 0, and a 1, and a 1. So whenever the clock pulses, it reads what the data stream is saying, and it puts that information into its own little cubbyhole in this little storage closet. So once that's done, being accomplished, and the data stream has been read, so the train has now gone into the tunnel, and this clock has allowed it to put all of the data, each bit, in its own little spot, then the latch pin gets set back high again. That closes the gate, and it pushes it into a new location that's kind of a permanent location, which is like pushing the data out of the end of the tunnel on the parallel tracks. So what this is good for is, instead of having to have 8 separate pins tied up in our Arduino, one to control each one of the LEDs, we can have all of our information come from one wire, and it comes out in the data stream, and then the clock and the latch do this little magic work of this, kind of imaginary tunnel that splits up the serial bit train into parallel individual bits, and then those can go down individual wires and go to our 7-segment display. Okay, so here's that chip that we were looking at, that 595 chip. Let's look at what each of the pins are for. First of all, let's look at the power and ground. So this thing here, VCC, that gets connected to positive 5 volts. And this GND, that's ground. So we're going to attach that to ground. And this provides the power for the circuit inside there so they can operate. Right under that, pin number 15, this is actually a data output. So this is one of the outputs from the tunnel for one of the cars in our bit train. Number 14, DS, if we look on the chart over here, DS stands for serial data input. So that's the data train. That's where that comes in. So the information that tells which LEDs to light up on our 7-segment display, that comes into pin 14 from our Arduino. Below that, number 13, it says OE with a bar over the top. OE stands for output enable, and the bar over the top means it's active when it's low. So if we want output to actually come out of the end of our tunnels, then we want to make sure that this is low, so we're going to tie this to ground when we wire it up. Below that, STCP, if we look on the code over here, number 12, that's the storage register clock input. So that is the latch pin. That's what's going to open up and close the gate to allow our train cars coming from the train to go into their individual tunnels. And then number 11 is the shift register clock input. That's the clock stream. That's the one that pulses on, off, on, off, on, off on a regular time frame and tells the shift register when to read the data. Below that is MR with a bar over the top. And if you look at what that means on the data chart here, it says that's master reset, and it's active when it's low. We don't want this thing to reset ever when we're doing our countdown sequence here. So we're going to make sure that it never goes low by wiring it to plus 5 volts. Pin 9, if you read what it says there, Q7 prime, if we look at pin 9, it says that's a serial data output. So this is a place where we can pass the train all the way through and have it come out as a train on the other side. We don't need that, so we won't use that pin. Okay, so Q0 on this side, remember that was an output. That's for bit 0 in our 8-bit train, our 8-bit byte. The other 7 outputs are on the other side. So Q1 through Q7, those are all outputs that are going to go to our 7-segment display to light up the appropriate LEDs to read out the digits that we want. So now if we think about how we're going to put this together, we already know that this is going to go to plus 5 volts. We know this is going to go to ground. She's not letting me draw this, but that's going to go to ground. This is going to go to one of our bits over one of our pins over here. So will Q1 through Q7. Those will all go to pins on our 7-segment display so that they light up the appropriate digits when the appropriate bytes of information are set in there. So Q0, pin 15, and then all of these on this side, those are all going to be outputs that will go from the chip to the 7-segment display. This will come from the Arduino and will be designated to the pin that's going to be our data stream. This will be the latch and clock pins from our Arduino. This one will be low. It'll be attached to ground, and it'll be attached to ground because we want to make sure that it does enable output. This will be attached to +5 volts because we want to make sure that it does not reset, and it resets when it's low. And then we won't use this Q7 prime pin at all. Okay, so here's what this looks like if we're going to actually build. Let me get rid of this drawing tool. You may want to take a screenshot or a picture of this for reference, but we'll go through this build together. It's pretty complicated. You can see on this build the items we've been talking about. There's this whole string of resistors, and those resistors are in between the outputs and the LEDs in the 7-segment display, which is there's the 7-segment display. Its pins are across the top and across the bottom. Those are the inputs and outputs. And then there's our chip right there, and then obviously it's attached to the Arduino. Okay, let's switch over to TinkerCad and start putting this together. Okay, let's start building. Here are the things that we're going to need. First of all, we need a breadboard. So search for that. Do not want a mini or a small. Definitely want a large breadboard for this. So there's a lot of components we have to put on here. Okay, so there's our breadboard. We're going to need an Arduino, obviously. Arduino Uno, that's the one we want. Put that in place. And I think I'm going to rotate this around so that it's like the one that we had on our drawing, just to make it easier to follow that for me, if not for you. And we'll need our chip. So let's find that. This was a 595 chip. There it is, shift register. So shift register, I'm going to actually install that probably about here. And I'm putting it across the ditch on my breadboard because I don't want the pins to be connected to each other. That would be bad. I'm going to need a 7-segment display. So let me 7-segment display. I'll put that maybe over here. It's a good spot for it, I think. And the little data dialog popped up here, and it says this is a common anode, but the one that we're going to use is a common cathode. Common anode means the high is positive and each LED has its own ground, but the one we're using, each LED is high, and the common is the ground. Okay, so now we have those in place. We are going to want 7 220 ohm resistors. So I'm going to look up, well, the resistors are right there. Pull this on and change this to 220 ohms. So I have to do this a bunch of times. So I will probably just speed through this real quick on the video. Okay, our resistors are in place, our chip is in place, our 7-segment display is in place. So now it's time to start wiring things up. First, let's do the outputs, just to get that out of the way, because this is going to be the messiest part of the wiring. So the 74HC595, the 595 chip is oriented so that the left-hand side is on the left-hand side. So it's got a little divot molded into the actual plastic chip if you were using this thing, and there's a little hole in it. That's just an orientation device so you know which pin is which. So our output, our first output, is going to be right here, output number 1. So that's the Q0 on the data sheet, And when I hover over it, this is kind of nice. The TinkerCad tells us which pin do we actually have. So that's output number 1, and that's going to go to our first of our series of resistors. So I'm going to connect there to there. And I'm going to try to be consistent with the drawing here as best I can. So that was blue on the drawing. I'm going to change that to blue. And then as I'm going, I'm going to try to do what I can to just keep things as neat as possible, just to make it easier to read. Okay, so it's going to go through the resistor, and then it's going to go to one of the pins on the 7-segment display. So this output 0 is actually going to go over here to this input for segment A. So we're going to connect to there. We're going to go over to that resistor. Maybe I just do that. And I'm going to keep that blue so I can sort of follow what's going on. Okay, so output 0 through the resistor that protects the LED, and it goes into the segment A pin on the 7-segment display. Okay, output number 2 is going to be this pin right here. That's going to go to the second resistor. So I'll click over here. Maybe I'll move that over one, and then kind of neaten this up a bit. I may be doing that. And then this is going to go, oh, that was orange actually in the drawing. So I'm going to change that to orange right now. And then this is going to go to this pin right here, which is segment B. So I'll connect to the output of that resistor, connect to segment B, or input for segment B. Change this to orange so we can keep track of it. And then I'm going to bend this like that, and like that, just to keep things kind of clear. Okay, so next, output 2, or sorry, output 3. So output 3 is Q2 on the chip. We're going to connect this to the third resistor. This was yellow colored on the drawing. Try and neaten this up a bit. This is kind of a hassle to do this, straightening the wire, but it's worth it in the end because it's hard to track everything. So this is going to go to segment C, and I think segment C is over here next to the decimal point. Yeah, that's segment C. So that's going to be connected to the output of this resistor. Change this yellow so it's easier to trace, and then put some bends in it. Whoops. Maybe like that. Next, output number 4, which is Q3 on the chip. Go to the fourth resistor. The color of this is actually white on the drawing, so I'll change that. Straighten this up a bit. There you go. So 4 will go to D, and I believe this is D right here, that's segment D. So the output from that resistor will go to segment D. Change that color to white. Bend the wire around to make it easier to track. maybe like that. Maybe I can move this down a little bit, make room for future wires. Okay, so now we got that taken care of. This looks a little bit messed up. I'm gonna smooth that up a bit. Okay, so next is output 5. So that'd be Q4 on the chip. Go to the 5th resistor. This wire was black, it looks like, or purple maybe on the drawing. And output 5, we're at ABCD, so we're probably going to go to segment E. And let's find out where we're at here. There's segment E. So the output to that resistor, right there. Change this purple for tracking purposes. Bend it around a bit. Okay, there we go. Next output, output 6. So this is going to go to F. Let's search for where that is. A common F. There's segment F. So that's where we're going to go eventually. But first we've got to go through our resistor. On the drawing, this was green, so we'll just leave that green. Neaten up the wire. And then from segment F, go to the output for that resistor, and then to here, and maybe over to there. There we go. Next output, output 7. Going to go to the 7th resistor. Oh, I'm missing a resistor, so I'm going to have to go back and fix that. Orange on the drawing. Oops. And the output from here would seem go to segment G. Right there. So that's going to go to the output. Orange colored. That. Okay, so that's all of the 8 segments that make up the digit itself. So the last output is going to go to the decimal place. So that's output 8 right there. We'll hook that to put it here because we don't have a resistor yet. And that was on the drawing yellow. Bend that down here. And there. And I'm going to grab my resistor, put that in place right there, change it to 220 ohms, and then connect it to the decimal point pin, which is right there, DP, yep. So now change that to yellow. Neaten this up. Okay, I think our wires are all connected now to the right places. And now we have to just do the special things, not the outputs and inputs. One thing, we want to connect our common cathode to ground. So right there is a common cathode, and straight across from it is another common cathode. So I'm going to just connect to this common cathode to the ground rail of my breadboard. I'll turn that black because that's what we do. And now let's go back to the chip. The chip has to be powered and grounded. So this is the power pin right here. It says power. So let's connect that to the positive rail of our breadboard. And we'll turn it red because it's positive. And then just bend it. Maybe like this would be adequate. And then we have to ground that chip. So we're going to go from here to the negative rail. I'm going to put it there. Turn it black. And then I'm going to get this purple wire. I'm just going to move it a little bit so we can see that connection. Yeah, so we have power to our chip. We have ground for our chip. Okay, some other stuff. We know that this output enable switch we want to go low because it's enabled low. So we're going to also hook this to the ground. And I'll make that black. Bend this wire up a bit. All right, made a wire I didn't want to make. Okay, so we have grounded the output enable. What else do we want here? This was the clear, the memory reset. We want that to be high because we don't want any resets to happen. So I'm going to tie that to the positive rail. And I'll make it red. Straighten it out. Okay, maybe like that. Okay, and this pin here was the serial data output, which we're not using. So clock, output register clock, so the clock pin and the data pin and the latch pin. Okay, so this is the data pin. And our data pin, we're going to use pin 2, digital output pin 2. So from there, we're going to connect to pin 2 on our Arduino, right there. On the drawing, this was yellow, so I'll change that color. And then just bend this up a bit. Pin 2. Okay, the next pin we're going to hook up is going to be this pin right here, the output register clock. That's going to go to pin 3 on my Arduino. So I'll connect that to pin 3. And it's green on the drawing, so I'll just leave it the way it is. And again, I'm just going to try and keep things kind of neat here, because it's messy enough even when it's neat. And then the last pin is the clock pin. So we're going to go from there to pin 4 is going to be our clock pin. And that was white on the drawing, so I'll change that wire color to white. Oops. And then one last thing to kind of neaten up. Gotta go up to here. And over to there, just for a change of pace. Okay, so now we have to power our breadboard and ground our breadboard, and then we're done. So here's plus 5 volts. That's going to go to the positive rail. Right there. With the red wire preferably, and then one of the GND pins we're going to hook to the ground rail with a black. All right. I think we have this all wired up properly, and now it's time to start writing some code. Okay, to begin writing code, you may have to eliminate some block and switch to text. Mine has already done that. So the first thing that we're going to do is we're going to establish a new data type here. This is a data type called a byte. So we already talked about a byte. A byte is a string of 8 digits. And then it's an array of bytes is what we're actually making. So I'm typing the word byte, and then I'm going to name this array. I'll talk about what an array is in a little bit. 7 underscore seg underscore digits is going to be the name of my array. Now, after naming in the array, I put an open square bracket, and I put how big the array is, and it's going to be 10. And so I close it. So that means what we're going to have is an array of 10 bytes. So that means an array is a data type, a single variable that can hold multiple values, and the 10 means that there are going to be 10 values in our array, and byte is a data type that's made of 8 bits. So remember, bits are ones or zeros. So our array is an array of 8-digit bytes. So now when we establish the array, we have to say what's in the array. So the next thing that happens is we go equals, and then instead of assigning a single number like we would with a float or an int, we have to make this array. So we're going to open curly brackets to do that. And then the first thing I'm going to do in here is I'm going to go B, and the B just says that this is byte 111 111 00. 111 111 00. So these are literally what we would want our 7-segment display to have high when we display a 0. So this corresponds to the output for segment 0. This byte does. So it's segment A, B, C, D, E, and F are high, and segment G and the decimal point are low. So then we put a comma after that, and then we're going to put the next bit. Now, I'm just making a new line here because the code doesn't matter, and I just want to help keep this straight a little bit. So next it's going to be B 0 1 1 0 0 0 0 0. So that's for if we want to display a 1. Remember, only segments B and C were on for that. Then B 1 1 0 1 1 0 1 0. That's the array for the letter 2, or the byte for the letter 2. Then B 1 1 1 1 0 0 1 0. That needs to be a capital B, I think. So that's for the number 3. For the number 4, the byte would be 0 1 1 0 0 1 1 0. For 5, it's 1 0 1 1 0 1 1 0. For 6, 0 0 1 1 1 1 1 0. For 7, 1 1 1 0 0 0 0 0. For 8, all ones except for the last one's a 0. So only the decimal point is off. And then for 9, 1 1 1 0 0 1 1 0. And that is the end of our array, and we put a semicolon after that. So that could have been, probably should have been, one line, but it doesn't matter, and this helps us kind of keep the digits all straight or individual from each other in case we have to go back and decode this, debug it. Okay, the next 3 lines are going to establish the pins, so we're going to have variables for that. We're going to name some pins. Int latch pin. So this is an integer variable. Latch pin equals 3, so that's saying the latch pin is pin 3 on the Arduino. And then int clock pin equals 4. And then int data pin equals 2. So the data train is coming from pin 2 on our Arduino. The clock pin is pin 4. The latch pin is pin 3. Okay, so that's the pre-setup stuff. So now we're going to do our setup. So we do void setup, open close parens, and then we're going to open up our curly brackets. So there's 3 outputs. They're the latch pin, the clock pin, the data pin. So we're going to do pin modes here. Pin mode, pin, or latch pin is output. Clock pin is output. Whoops, doing this wrong. Pin mode, clock pin, output. Not sure it's why it's indenting for me all the time. And then another pin mode, data pin also an output. And I think I forgot to put semicolons up here. May as well straighten that out while I see it. And that is the whole entire setup. So we'll close the curly bracket out for that. Got some funny indentation going on. I'm not sure why. So now let's put in our loop. Void loop, open close parens, open curly bracket, and then we put our loop in. The loop is actually going to be super short because all we're going to do in this loop basically is call something called a method, which is a little thing like setup or loop that we write ourselves that gets called from the loop. So here's the command here. It says for, and then it's going to make a byte that's part of the for loop, and we're going to name the byte digit equals 10, and then a semicolon, and then we're going to put digit greater than 0, and then another semicolon, and then minus minus digit. Okay, so let's talk about what this means. It establishes this byte, this variable called digit, that's a byte type, and it says digit equals 10. That's a starting point. Digit greater than 0 is an ending point for our loop, and then the minus minus digit means every time you go through this loop, this for loop, you're going to make the value of digit 1 smaller than it used to be. So this is a for loop, so we need to know what do we do for that time. So we put an open curly bracket, and the first thing we're going to do is a delay for 1,000 milliseconds. And then we're going to do this thing here. 7 capital seg capital right, and then in parentheses we're going to put digit minus 1. Okay, Okay, so here's what this does. This 7-segment write, or 7-seg write, that's the name of a method that we're going to write later. And it's going to send the value of whatever digit is less 1 to that method, and then that method is going to do something. And a method is just a set of commands that we put information into, information comes out of it, and gets sent back to the loop. Okay, then we're going to close this. For loop, and then we're going to delay for a second, and then we're going to close the loop. Okay, I went and put that byte declaration all in one line, and that shifted my indents all over so they're a little bit more reasonable. Might make it a little easier to read this code. Okay, the one thing that we have left to do now is we have to establish what that method is. That's called 7seg write. That gets called in void loop. So here's how we do that. We type void. So it's like void setup or void loop, except it's void 7seg write. So this is not. This is the method that we named 7seg write that we're calling in the loop, and unlike open close parentheses like on loop or setup, this actually has an argument to it, which means the information that gets passed into the loop or into the method. So that argument is byte digit. So that's the value from the loop that gets passed into this method. So we open our curly brackets to establish what is going to be in this method. So the first step in the method is we're going to write the latch pin low. So we do a digital write and then latch pin low. So remember, writing the latch pin low opens up the gate and allows the individual bits to be pushed into their little storage locations. And then we have a command here that will push those bits in. So that is a shift out. This is a command from Arduino. And then the arguments are first, where's the data stream coming from? And that is data pin. And then where's the clock? And that's clock is going to be on clock pin. So it's looking for those two things, so it knows where to get its information. And then the next thing is, what order is it going to send the bits in? And if you want to go from right to left, then you would do least significant bit first. And if you want to go from left to right, you would go most significant bit first. We're going to do least significant bit first. So that's LSB for least significant bit, and then the word first. So this says read the digits from left to right as you push them into the storage locations. And then where do we put them? Well, we put them in this array called, that we declared earlier, 7_seg_digits. And then in each array location, we put the value of the byte digit that was declared earlier. Close paren, and then close the line out with a semicolon. So this moves the data into the register, least significant bit first, reading the data off data pin, the clock off clock pin, and putting it in the array named 7seg digit with each digit. So the digits are going to count down from 10 to 1, and then we're going to write the digits 10 minus 1 down to 1 minus 1, so in other words 9 down to 0. Push those bytes into the shift register, and then those will be pushed out onto the 7-segment display, and it should display what we want it to display, readable digits as it counts down. And it's going to do this once a second because we have a delay of 1,000 in the middle there. And then the last thing, we have to write the latch pin high again to close the gate and push the information out. So that'll be a digital right latch pin high. Oops, got my parens wrong. Okay. And that's the end of the loop. I mean, of the method. So we'll close that out with a closed curly bracket. Now let's see if it works. Okay, it looks like we got some problems. 7-seg digit was not declared in this scope. So probably it's a spelling error. Yep, I declared it up here at the beginning as 7-seg digits. So I got to put S on the end of that. Let's try it again. Okay, the simulation's going. I'm going to move the code out of the way. You can see it's counting down from 9 to 0, like it's supposed to. So the data's coming, remember, out of this pin 2, down that wire, the yellow wire, into this chip, and then the chip is reading that data according to the clock information that's coming off the green wire, and the latch pin that opens it up, open and close, that's, I believe, the white wire here. So it's doing that, sending serial information, it's being transferred to parallel, and then sending information out of the wires, and then turning on the correct segments to count down. Now, if I hover over this, it says this device broke. It's hovering over the chip, which has a flash on it. So apparently, if I had done this in real life, they're saying I would have burned out this chip because the total current is too big, 50 milliamps max, and it's at 61.9 milliamps. But I will tell you that I have wired this up many times in real life, and I did not burn out that chip. So I'm not exactly sure what's wrong there. Maybe we need to reduce the voltage coming into the chip by just putting a big resistor on the whole input to the breadboard. But at any rate, the code is doing what it's supposed to, and the basic wiring looks good, although according to them, we do have some kind of a problem with power overdoing the chip. So hopefully you learned a lot. Maybe some of this is still sketchy to you, but if you look through the code and kind of review what each line did, maybe you can get a feel for how this works. Some independent projects are going to ask you to expand on this, so don't get rid of this code or this wiring, because you can recycle them for a future project.